Hello, algebra students. This is looking at lesson 2 of unit 6. We're going to graph some simple rational functions. So first, to define a rational function is a function that is of the form that you see over here. Important thing is that the word rational, root word is ratio, and ratio means fraction. So a function is a rational function if we've got a variable in the denominator of a fraction. So we're going to call it q of x, some polynomial denominator, p of x, some polynomial numerator. If we've got x's up here, that's fine too. The key is if there's x in the denominator, it's a rational function. Okay. Most simple rational function we have out there would be 1 over x. And that would be the parent function. Take a look at 1 over x. I want to pull up Desmos and take a peek at what 1 over x looks like. So here I have it graphed for you. A couple important things that are going on here. This particular shape is called a hyperbola. So hyperbola, okay, not hyperbole, that's an English term, hyperbola, A for algebra. Anyways, the reason that it looks the way that it does, if you check this table out over here, is that when I plug in 0, 1 divided by 0 is undefined, doesn't exist. And if you'll notice as you look at this graph, there is a vertical asymptote here at x is equal to 0. So the vertical line x equals 0 is a vertical asymptote for this function. Okay, can't plug in 0. Then as I plug in 1, I get 1. 1 divided by 1 is 1. 1 divided by 2 is now 1/2. So I got 1, I got 1/2. You know, if I were to go up this a little bit and plug in, let's say like, if I plug in 1/2, for instance, notice that I get, I'm really close to 2. 1 divided by 1/2 is 2. Well, the thing that you'll notice is that as x gets bigger, the y value gets smaller and smaller and smaller and smaller, and eventually gets really, really close to 0. Does it ever get there? No. Because I plug in something, I plug in 10 million, let's say, 1 over 10 million still exists. It's still not 0. It's really small, but it's not 0. Okay? Same thing goes on the other side. This is the first branch of my hyperbola, and then I got another branch of my hyperbola over here. When I plug in -1, I get -1. When I plug in -2, I get -1/2. When I plug in bigger and bigger negative numbers, I get smaller and smaller negative numbers for the output. As I plug in smaller negative numbers, once it get closer to 0, notice that the output gets bigger and bigger and bigger in a negative fashion. So remember, I can't plug in 0, but I can plug in anything that's a little bit bigger than 0 or a little bit less than 0. And it will give me a really big positive output or a really big negative output. Okay. So I've got a vertical asymptote, like I mentioned, at x equals 0. And I have a horizontal asymptote at y equals 0. So I can't get 0 for an output. Okay. Keeping those ideas in mind. Back to our notes here. I said the graph's a hyperbola. I said that there's a vertical asymptote at x equals 0 because I can't plug in 0. I said there's a horizontal asymptote at y equals 0 because I can never get 0 for an output. Domain and range, well, my domain would be all real numbers except the one that I can't plug in. Remember, this is related to the x values, which in this case are the vertical asymptotes. So all real numbers except 0. Okay? And here, all real numbers for the range is all real numbers. I can get any y value I want. All real numbers except 0 as well, because that's where the horizontal asymptote is. Okay? Now, what we're going to do is we're going to take our parent function. We're going to move it around by using our friends a, h, and k. Okay? H and k do the same thing they've done for every other function that we've looked at. A is going to make our graph get skinnier or fatter. It's going to maybe flip it over the x-axis. H affects the x value, so that's going to slide our graph to the right and to the left. And k affects the output, so that's going to slide our graph up and down. Okay, it's going to shift our graph in all sorts of different directions. So I want to show you that by showing you my slider that I've got down here. So I'm going to turn on this function. Right now I have a set to be 1 and h and k are both 0. So essentially I'm graphing 1 over x, which is the same as the blue. That's why nothing shows up. Now when I hit, I'll get rid of the blue just so you can see it. Yay, same graph. See? Yay. With it turned on. When I hit play, watch me mess with a. A is the number on top, so a is our constant that we're dividing by x. When I hit play, notice that it stretches my graph out as it gets bigger positive, and then when it becomes negative, it reflects across the x-axis. So this branch goes down here, this branch goes up there. And again, it stretches away from the origin, and as it gets smaller, it comes back. Positive flips back over, it goes into quadrants 1 and 3 again. Now, if I set this back to 1, watch what happens when I play with h. So h is the number in the denominator that affects x. I hit play. As h is positive and going to the right, and now as h is negative, it's going to the left. So I'll pause it somewhere right about here, let's say. So h is 4.66. That means in my equation I have 1 over x minus 4.66. So with h, I use the opposite of what I see. I would be seeing x minus 4.66. Well, 4.66 is where the vertical asymptote is. Look at that. So it used to be at 0, now it's at 4.66, because that's the value of h. Okay? I'll put that, I'll make it negative. So further and further to the right, comes back to the left. So right now, h is negative 4.33. So I would see x minus negative 4.33, which would really be x plus 4.33. So use the opposite. Negative 4.33 is what makes the denominator equal 0. Therefore, negative 4.33 would be the vertical asymptote. Enough messing with that. Put that back to 0. K is the number on the outside. K gives us our vertical shift. So I hit play on K. It shifts my whole function up. And when K is negative, it goes down. Okay. And what that means is that it's shifting the horizontal asymptote up and down with it. So whatever K is, in this case, K is negative 2.9. That's where I'd have my horizontal asymptote. Because I'm going to get something close to 0, but then I'm going to subtract 2.9 from it. So I'm going to get something that's close to negative 2.9. Okay? And with K, I keep the sign of whatever I see in the equation. So here now K is positive 3.5. Well, that 3.5 is where that horizontal asymptote is. So that's graphing some simple rational functions with vertical asymptotes and horizontal asymptotes. Give you a quick idea, and you can play around with that in your notes.